Hey, what's up, guys? Back with another video on developing our real-time scheduler for the PIC16 microcontroller. You know, that mimics Arthur's functionality. And we're here on scripted, and I'm going to be talking about mutexes. When you have an Arthur's, sometimes when you have shared resources, we need to protect those resources. And to protect those resources, we need a way to avoid simultaneous access by multiple threads, or in this case, multiple tasks, interfering with those having conflict with the shared resources. And a mutex is like a lock. So when a thread or process wants to access our shared resource, we have to get, a mutex or a lock associated with the resource. And if the mutex is held by another thread or process, usually we'll do something like we'll block the thread until the mutex is released, or that's what we usually do in a system like that. And we also need a system so that when, like a thread is finished accessing a resource, that there's a release mechanism in place. And also when the thread is accessing the resource, that it enters a critical section in the code where, it could safely access the shared resource without interference from the other threads and processes. And this mutex type system prevents race conditions from occurring. Now, implementing a mutex is a very complicated endeavor. When you think about a mutex and what it's trying to accomplish, on the microcontroller we have a special advantage because we have access to interrupts. And our entire scheduler so far is interrupt-based, and we can take advantage that we have access to interrupts, to implement our mutex. So this is the mechanism I came up with for implementing the mutex. So we added a mutex to give our mutual exclusion and ensure the thread safe access. So the first thing we do when developing our mutex is that we find a type alias for the mutex. This type alias will represent the state of the mutex. Then what we do is we define context for the mutex state. This constants will be a 0 for unlocked, a 1 for locked. And the way we do the mutex locking and unlocking is with these two functions here. And what we do is we disable interrupts and enable interrupts for the mutex lock and the mutex unlock mechanism. And by doing this, by disabling interrupts during the critical code section, we maintaining the automaticity of the code. It remains atomized. And how we do integrate this automation system is that when you perform our enqueue and our dequeue sequences within the function, what we do is that Dex will lock the mutex before accessing the queue. And I also added some overflow handling here as well within the queue. And with this overflow handling, when the overflow condition occurs, we'll override the oldest value in the queue. And I also, we lock the mutex and we unlock the mutex after accessing the queue. For the dequeue function, we did the same thing. We lock the mutex and we unlock the mutex after accessing the queue. And the way I handle overflow is basically, all I did is we just set the value to 0. And what we have here now is a very thread safe type of queue structure for messaging, for our message queue, because by adding the mutex to lock and unlock before accessing the queue, it ensures only one thread can modify the queue at a time. and we gain prevention of race conditions, and we gain our thread safety. So I hope this video was helpful in letting you see how we could add a Mutex to our real-time scheduler and our resource constraint system. I experimented adding more, a more complex Mutex mechanism like you typically find in narrators, but this type of structure is sufficient considering the constraints of the system. So in the next video, I might further look at more error handling. So that's it, guys. Thanks for watching. Be sure to like, share, and subscribe. I'll see you in the next video.